We're good to go. I'm going to speak much faster now that we have less time. OK, so this is about train faster, generalize better, or speak faster, generalize better. Stability of stochastic gradient descent. So, Andrew told you it's all about scale. Jan told you it's all about unsupervised. I'm going to tell you it's all about stability. All right. So this joint work with Ben Recht from Berkeley, who's part-time at Google now, and Yoram Singer at Google. All right. So this talks about stochastic gradient descent, or SGM. I'll call it stochastic gradient method, which is the simple optimization technique where you're trying to optimize or minimize an objective function which decomposes into n terms, and each term only depends on one of the points that you have, and the joint optimization variable is w. Okay, so it's just a quick recap. Probably most of you have used this all over the place. So the way it works is you start with an initial guess for what your parameters should be. Let's call that w0. And then at every step, you update your parameters using a simple gradient step. So you subtract the gradient at your current parameters, multiply times the step size. But you only compute the gradient with respect to one of your data points, which is what makes this much faster than taking full gradients. Okay? So this is the stochastic gradient method. And many of you know that stochastic gradient is really effective for machine learning. It's sort of the default method in practice. It's scalable, easy to implement, robust. It works well across many different domains. And so it's the first thing you usually try. Okay? So the way you apply this is that the function f captures your training loss, or some loss function of the model described by the parameters w on n training examples. And you imagine that these training examples are drawn IID from some distribution D. So there are two fundamental quantities in machine learning. One of them is the empirical risk, or training error. That's just the average of your loss function on your training set. This is what you can minimize. It's an observable quantity. It's something you can evaluate, and you can minimize it using SGM. What you should actually care about as a machine learning researcher is your test error, or population risk, which is how well your model is performing on unseen examples. Okay? So minimizing empirical risk by itself is not interesting. What you actually care about is having small loss on the distribution from which the samples were drawn. And this is, in general, an unknown quantity, so you don't know it. You can't evaluate it easily. Okay? So the fundamental notion that connects these two quantities is the generalization error. Okay? So it's just the difference of the population risk and the empirical risk. It's telling you how much does your training error underestimate your test error. Do you think your model is good based on the training error, but it's actually bad? This is what the training error, what the generalization error captures. Okay? So in other words, if you're a very skillful machine learning researcher and you got your training error down to close to 0, all that matters at that point is what is your generalization error. Okay? So if you optimize well, all you care about is generalization error. Good. So here's a simple example, state-of-the-art problem separating triangles from circles and in the plane. And here's one solution you could come up with. And of course, you should kind of be annoyed by this solution because it looks like a terrible solution. So what's wrong with it? Well, the solution has huge generalization error. All right, so you're carving out all these triangles and you're missing out all the circles. You have probably pretty good training error, but if you sample new examples, it's going to be terrible. Okay, you're going to have huge loss. So there's a big difference between training and test error for this model. But you might say, well, this is not what SGM could come up with, right? So SGM would do something like this. It would start with some solution, let's say a randomly chosen hyperplane. And at that point, you have small generalization error. Why? Because your model is completely independent of the data. So there hasn't been any chance of overfitting yet. Okay? It's independent of the data. So whatever the training error is, it must be close to the test error. It might be high, but it's, the generalization error is small. And so you go on and you optimize, and maybe your hyperplane gets better from the point of view of training error. But what you observe when you inspect these intermediate solutions is that SGM will always have small generalization error. Okay, so you look at these solutions, and perplexingly, they all have small generalization error. You can keep going for a while, and they will have good generalization error. The training error might change, but the generalization error is always small. So we're looking at this, and we're wondering, I have 3 minutes left. Okay. This was unfair. It was not my fault. Okay, so this is really about speaking faster. Okay, so good. So we were wondering is this a coincidence, and no, it's not. Okay, so any model trained by SGM with a reasonable number of steps has vanishing generalization error. Okay? So what does reasonable mean? It's somewhere between n and n squared, which is where all the action is happening in practice. So if you make not too many steps, but you can make more than one epoch, you can make more than one pass over your data, you can make, let's say, 100 passes. If you're in that regime, which is where all the action is happening in practice, you must have small generalization error. You cannot overfit with SGM. Okay, so this applies to both convex and non-convex losses. These are theorems you can prove, or we prove in the paper. There are some assumptions. Your loss function must be smooth in Lipschitz, but it basically, this is the upshot of what the theorems say. I find this very interesting because the traditional view is that generalization error must scale with model complexity, VC dimension, something like this. But if you look into practice, this is sort of not what's really the dominating factor, or not what's the explanation for why you have small generalization error. And one area where that really pops up is artificial neural networks. It's responsible for these pictures and many Facebook, iPhone apps I saw this morning. And so if you look at these, at research in this area, and you don't have to go very deep, it happens already on MNIST. If you train a model on MNIST, just a 2-layer model, you'll see that the generalization error is very much a function of the number of epochs. So as you train for more and more epochs, and epoch is a full pass over the data, it'll go up. But if you do that for many different hidden units, so 100, 200, 400, 800 different units, so as you scale up your model size dramatically from 100 to 1600, the plots you get are all the same. Okay, so you really see that generalization error is a function of the number of steps, but not of the model size. Okay, and this is exactly what our theorem formalizes. So if our approach is not VC dimension, what is it? It's stability. Okay, so we show that SGM is stable under small perturbations of the data. So if you slightly perturb your input set, you replace one point by another, your training loss is well behaved. This is stability. It's well known, or has been known for a while, that stability implies generalization. It's a beautiful line of work, one of my favorite lines of work in machine learning. And we only contribute that SGM is stable, which I think is interesting in its own right, because it's a new robustness property of SGM. But it has this very nice application to generalization error. Okay, so just wrapping up, 1 minute. Do I have 1 more minute?
It depends on whether you want questions or not.
I want questions. Okay, but maybe the questions in the coffee break. Okay. Okay, 1 more minute. So if it's all about stability, right? If stability implies small generalization error, can we make SGM more stable, maybe by tweaking the model architecture, by designing better models? And the answer is yes. In fact, others have already done that for us. So you look at the tricks of trade and deep learning and other areas, and you find out that a lot of the operations people do are stability inducing. So they make your model more stable. Weight decay is one example, dropout, gradient clipping. Okay? And again, I find that very interesting that some of these things that work well in practice are actually stability inducing. It makes me wonder, can we find more stability inducing operations? Here are some suggestions. Gradient distraction, drop det, long weight, short decay. So, you know, my point is I invented them. They don't actually exist, also not at Google. But my point is there's a huge design space, and deep learning people are amazing at coming up with names like this. There's this huge design space that we haven't explored. And maybe stability is a good way to explore this design space, right? Maybe we should be looking for things that make our models more stable. And by doing that, we will find better or new architectures. Okay, so can stability help? That's all I wanted to say. Thanks.
All right, so we're gonna take questions until the next speaker is set up. And based on previous experience, this might give us 9 minutes worth of questions. Are you the next speaker? Hey, how's it going? All right, any questions for Moritz?
So how important is the separability?
Wait, microphone.
Sorry. How important is the separability assumption relative to the samples for this?
You don't need it. It's not an assumption in theory.
Okay.
So model complexity.
You want to speak to that mic? Sorry, you want to speak to that mic?
So he asked if separability is needed for the theorems. No, it works for the unrealizable case as well.
All right, let's take one more question.
One more.
How about local optimum for non-convex loss functions?
Yeah, it's perfectly fine because
Can you repeat the question? Sorry.
Yeah, so the question was, what about local optima for non-convex losses? It's perfectly fine for us because we're not talking about optimization. I'm not proving that SGM is guaranteed to converge to small training error. That's another question. That's a very hard question. We don't know what to say about it. But what I'm proving is that it must have small generalization error. So whatever the training error is, it's close to the test error. So I don't care about local optima. In fact, that's great, because you're going to be more stable if you get stuck. But
all right, let's thank the speaker again. All right, I'm very pleased to introduce David Helmbold from UC Santa Cruz, who is going to talk about the dropout bias.
Thank you. This is joint work with Phil Long, who's now at Sentient Technologies, and it's based on our paper that's on arXiv and to appear in JMLR. So some of you may not know what dropout is. It's a method for training neural networks that's popular in the deep learning community. It's stochastic gradient descent with a twist. Basically, you take some nodes in the network and you deactivate them for the stochastic gradient descent update. So when you train your first example, you might compute things and update weights based on this reduced network. And your second example would have a different reduced network that you'd be training on. Why is it interesting? Well, Hinton in the 2012 ImageNet competition, his group won the competition by a tremendously wide margin, and he identified dropout as a key contributor to their group's success, and it's had several successes in other domains since then. It's also a little mysterious in that why would this corruption of your network be a good thing to do? It's sort of like a bug in some grad student's implementation that seemed to have a beneficial effect. Well, the question that we're interested in doing is doing some analysis to try and figure out what this dropout training does in terms of sort of regularization. How does it pull the weight vectors you learn? We know that L2 regularization tends to prefer short weight vectors, pulls the weight vector to be shorter. L1 regularization tends to pull sparse weight vectors. What does this dropout tend to do to the weight vectors when you learn with dropout? So we're asking sort of qualitatively or analytically how dropout pulls the vectors, what direction, rather than how much and what's the effect on generalization, which has been studied by a couple other groups. So our framework, deep neural networks are hard for us to understand exactly how they work, so we'll do something a little simpler. We'll do linear classification with convex optimization. And this would be like what would happen at the deep node, what would happen at the output node of a deep network. And if we can't understand just a single node's behavior, understanding how it works in a deep network is sort of a lost cause. So the other advantage of looking at this convex optimization framework is there's no local minima. So we can identify the pool of the dropout method independent of the optimization strategy, which may direct you to one or another local minima. We're also interested in the bias of the dropout method rather than the variance. So we want to abstract away the sampling issues and assume we have a base distribution P over labeled examples and consider the minimizer of the regularized loss or criteria with respect to this distribution. So this base distribution could be the distribution that generates the sample, or it could be an empirical sample distribution, or by looking at different distributions, it could be a way to say, how does dropout pull differently on different samples? So the loss proxy for classification we have is the logistic loss, and for a source P and dropout probability Q, dropout will produce a vector W star of PQ, which will be the minimizing W for this dropout risk. And this dropout risk is an expectation of the labeled examples drawn from distribution P, and an expectation of which things get dropped out of the logistic loss of the W dot dropped out X product with the label. So dropout has been viewed as a regularizer by Weger, Wang, and Liang, and they show that the dropout risk of W can be broken up into two terms, into a expected loss without using dropout on the undropped out examples, plus a reg D term that's a dropout penalty for the weight vector that you're using. And this reg D term is adaptive. It depends on the instances in the sample, but not on the labels. So that promotes its use as a regularizer. We can separate out the dependency on the labels for the dropout risk and a contribution that does not depend on the labels. And using some approximations, they show that dropout regularizes something like an adaptive two-norm regularization. However, we look at the exact dropout penalty and refine that a little further. So some properties of this dropout penalty is it's non-negative for all W, it's 0 at the 0 vector, and since the logistic loss at the 0 vector is 0, if the regularization is bigger than ln2, then that weight vector won't be the optimizer of the dropout criterion. Dropout has some strange properties also, that if you take one weight and set the other weights to 0, then the dropout regularization penalty remains bounded. That's a lot different than how L2 regularization behaves. Except for degenerate cases, when you send two weights to infinity, the dropout penalty will diverge, and that shows that the dropout regularization penalty is emphatically not convex. In fact, it cannot be approximated to within any constant factor by a convex function. On the other hand, the dropout risk, the combination of the logistic loss plus the dropout penalty, is a convex function. So it gives you a way of adding a non-convex regularizer, but still leaving you with something you can optimize. If your distribution over features is concentrated on the 1-1 vector, then the dropout regularization penalty is not even monotonic in the individual weights. That you can increase a weight from 0 and the regularization penalty will decrease. So what we're interested in is what sources are or are not compatible with dropout, and dropout sort of partial answers to this, or dropout encourages the use of rare but reliable features. And empirically, Srivastava has noted that dropout limits co-adaptation. It tends to learn networks where units learn simple functions of their inputs. More precisely, we postulate a definition for co-adaptation where a weight vector W1, W2 is co-adapted for some source P. If the weight vector is good, it has loss less than the 0 vector. But if you drop any of the weights and turn it into a W10 or 0W2 vector, then you get weight vectors that are bad, worse than using the 0 vector, have higher loss than the 0 vector. So for example, if we had 4 data points, 2 labeled minus and 2 labeled plus, there's a Bayes optimal set of weight vectors that'll predict optimally on those. But the feature vectors, the features are highly correlated. And when the features are highly correlated, dropout wants to put similar weight on both of them. So to get to the Bayes optimal weight vector like 5 minus 5 that has small expected loss, dropout will avoid going there. This co-adaptation, the expected loss of 5, 0 and 0 minus 5, will predict badly on some of the examples and have high loss, much worse than the loss of 0. So a hard goal is to characterize the sources where dropout's weight vector is close to Bayes optimal, but this is a very ambitious and difficult goal, and it involves the issues of close compared to what, and is the closeness due to the underlying source distribution P, or the fact that you're having a low Q, not dropping out much stuff, and not regularizing very hard, very strongly. So as a baby step, we can compare the dropout regularization process with other well-known regularization processes like L2 regularization and find pairs of distributions that separate the two regularizers in the sense that the one regularizer's learned weight works very well in one source and poorly in the other relative to the other regularizer. And we'll use generalization error to measure the success of learning. So as an example of separation, we could have 3 points in a P distribution, with 1 point having low probability, and 3 points in a Q distribution. And for these pairs of distributions, we can run dropout with the same Q dropout probability and run L2 with the same lambda regularization parameter and see what happens. And it turns out for the first distribution, dropout produces a Bayes optimal hypothesis, but the error of the L2 regularizer is a 7th. And for the second distribution, the dropout produces a hypothesis with error 1/3, and the L2 produces a Bayes optimal hypothesis. Why does this happen? In the first example, for the P's, you've got a example out here that's pulling your weight in the first component to be large. But you've also got a high probability here that's pulling the weight in the second component to be large. L2 tries to find a short weight vector with 2 large components and fails to get this bottom example correct. On the other hand, dropout doesn't like spreading weights out when the features are not correlated. So dropout will pick this dimension actually and emphasize this and put a long weight here, and the dropout regularization will prevent adding extra weight to the second component and get the Bayes optimal predictor. And similarly, in this example, the feature vectors are highly correlated. The signs of the feature values are different. And in this case, dropout strongly wants the weights of the feature values to be different, to agree with how the feature values are correlated. But here, the optimal weight vector will be a weight vector with 2 positive components. These 2 examples here are just above the diagonal. And L2 can find that weight vector, but dropout can't. Okay, any questions?
So we have time for 2 or 3 questions. Microphone over there, please.
Seems like a sparsity encoding prior that's adaptive in some way. For example, maybe that might be
Dropout.
Could you repeat the question?
It seems, so the question is, it seems like a sparsity encoding in some way. The dropout penalty is complicated, but it does seem to prefer single dominant explanations when the input values are not highly correlated. So yes, yes, but it's data dependent as to how strong that is. Can I get the slides back on, please? So when the data is highly correlated, you don't like to go in the anti-correlated, and when the data is not highly correlated, the dropout penalty sort of prevents you from going to using multiple weights strongly.
Any other questions? Mm-hmm. Okay, then we're going to thank the speaker again.